Okay, let's start. Good afternoon. So this week we're going to keep working on dimension theory. We're going to switch over to sort of more analytical notions of dimension as opposed to more topological notions we covered last week. One example of this so-called Lebesgue covering dimension. Recall that was some notion of dimension that gave an integer, if at all, to subsets, or metric spaces or subsets of metric spaces. But we want something more fine. So we want some notion of dimension, or a couple perhaps, that give fractional numbers as outcomes. Before that, I want to say a couple more words about this Lebesgue dimension, and then we'll switch over to what is called Minkowski dimension. So in the book, it is called fractal dimension. Elsewhere, you can hear the word box dimension. They are basically the same thing. And there's another important dimension which we sort of mentioned a couple times, the so-called Hausdorff dimension. Now, Minkowski dimension and Hausdorff dimension are sort of similar in a sense, but today we're not going to be able to see why they're similar, but they are in a sense similar. Why don't you pass the candy over there? Yeah, please take as many pieces of candy as you want, because we have 9 people. So, and I don't want that anywhere near me. So, okay. So first, let me remind you some stuff. So, let's say that I have a subset of a metric space X. What was the Lebesgue covering dimension? We denoted this by this. And so this is the min of all integers n, such that for any open cover U, so it's a cover of A using open sets. There's an open refinement. V, so this is sort of like your initial pixeling, or pixelation, let's say, and then you sort of like refine your pixels. Even though I'm using the word pixel, I'm allowing two pixels to intersect, and that's sort of like the point of this Lebesgue covering dimension, such that the multiplicity of this refinement is exactly n plus 1. And so what was the multiplicity? Well, it was the number of intersections, basically. So I fix initially a point x, and then I look at the number of v's, so subsets, in this cover, such that x hits v. And then I take the soup over all x's. And all a's. So this was the multiplicity. And so this was the dimension. So the empty set, so if I were to take A to be the empty set, well, this is sort of like a silly thing, but the dimension turns out to be -1. And the dimension, so the Lebesgue dimension of finitely many, or a finite set, is 0. So exercise. So let's say x1 to xn. It's a finite set. That's 0. And there are many other sort of computations you can do. What is, sort of like more generally speaking, what does it mean for a subset to have zero Lebesgue dimension. Based on this definition, heuristically, that should mean something along the lines of, you take your set, and then you get to cover it using open balls or open subsets of arbitrarily small diameter, let's say, that do not intersect, right? Because here in the multiplicity, I'm counting the number of intersections. And so dimension being equal to 0 in the context of Lebesgue covering dimension means that you get to cover by things that don't intersect. So in a sense, that is some notion of disconnectedness. So let's just write it like this. Can cover A by arbitrarily small open subsets that don't intersect. Okay? And so here's an easier here's a better argument as to why the interval has Lebesgue dimension 1. I sort of gave in, I discussed this last week, but I don't think I did a good job. So I claim this. So first of all, what does this mean? It means that the dimension is at most 1, and it is at least 1. Okay? That is to say, the dimension is at most 1, and it is larger than 0. And in a sense, if you believe this, it's rather reasonable to expect that the dimension, Lebesgue covering dimension of the interval, should be a positive number. Because there's no way you can cover the interval using open sets that don't intersect. That's sort of disconnectedness, okay? And the interval is connected. So I didn't define this notion of connectedness in this class, but it's a definition that is in Barnsley if you want. It's not super important for our purposes, but it's still important in general topological situations. Cannot be 0. Okay? I should not expect to be able to cover the interval using disjoint open subsets. But I can say something along the lines of, the dimension must be at most 1. So, because I get to take this minimum, right? So, because, well, in this definition, this is also somewhat of a logical thing. But, well, U itself is a refinement of itself, right? This is sort of like a bizarre thing to say, but it is true. And so if I can come up with one cover such that, so in order for dim to be equal to 1, multiplicity has to be 2. That is to say, at most, any 2 cells in my cover should intersect. And that I can do. I can just look at sort of this open covering. Okay. And so that's sort of like a better argument as to why the dimension, the Lebesgue covering dimension of the interval is 1. Now, if you try to do the same thing in higher dimensions, it turns out to be not that straightforward. The upper bound, like I mentioned in the beginning of this class, is rather straightforward. But for the lower bound, you need some technology, okay? So perhaps before that I should give an exercise. Namely that Lebesgue covering dimension is a homeomorphism invariant. That is to say, if I have two metric spaces, and if there's a homeomorphism from one to the other one, then they have to have the same Lebesgue covering dimension. This doesn't work the other way around. That is to say, you cannot just deduce that two spaces are homeomorphic. There's a homeomorphism from one to the other one, purely based on the information that they have the same dimension. That is not true. But at least it goes one way, and you can, you can sort of think of this in the contrapositive way as well, and you can say, oh, I have these two metric spaces, and somehow I get to compute their dimensions. If those dimensions are not the same, then there's no homeomorphism between them. Okay. So, example, dimension of Rn. It is true that this dimension is n, okay, but it is not straightforward to do the lower bound. This rather straightforward. And the way you do this is by sort of coming up with a nice cover like I did over here. And so this was Lebesgue's original idea. He used basically bricks. Okay, so imagine sort of like a brick wall. So in the case of n equals 2, you want a cover such that at most 3 cells intersect. Cover at most 3 of whose cells. I think this is grammatical. And so here's the idea. So I want to cover the whole plane when n equals 2. And I'm going to take, imagine sort of like, I have like different sort of heights, and I'm going to take little rectangles. Let's say like this. And in the next stage, I'm going to stagger them a little bit. And then stagger them again, and so on. Now these are closed rectangles, but I want an open cover. But one thing you can do is you can take each of these cells and take their sort of doodle around them, right? That is to say, take their epsilon neighborhood, so that you have, instead of, for instance, this sort of closed set, you have an open ball or open set. That is the doodle. Okay. And then, for instance, if I were to take this, it turns into something like this. And then this turns into something like this. And of course, as I'm doing this, I can take these cells to be arbitrarily small if I wanted. The point here is that any point on the plane sometimes is in exactly 2 cells. For instance, this point over here. So here, this particular point is in exactly 2 cells. But if I were to look at, for instance, this point, it's in exactly 3 cells. And there are no points that are in the intersection of 4 cells, because any 4 intersections is empty. Okay? So this gives you the upper bound. It doesn't give you the lower bound. Okay? The lower bound is, so I was reading Piston and Klimenhaga's book, and they say, oh, you know, the Lebesgue covering dimension of Rn is easily seen to be n, and so on. But for that, you need some sort of algebraic, at least, sort of technology. You need to develop some machinery. So let me just say here, the lower bound, while it is true, this statement is at least as complicated as what is called the invariance of domain because of this property. So you need some algebraic topologies, typically sort of the way to go. The invariance of domain is sort of like a standard important theorem in topology, which says that Rn and Rm are homeomorphic if and only if n equals m. And once you have that, you have this too, ultimately. Okay. Good. Okay, I'm not going to say anything about that. Good. Any questions about any of this?
So
yes.
when you have that, then they basically just say, oh, it's not homeomorphic with anything less than n, and we have an upper bound for n, so then that guarantees that its lower bound is n as well.
No. Well, you need to. I think the main issue is that, so I'm just thinking of the proof of the invariance of domain. So the hard problem is that if you have a homeomorphism from Rn to Rm, how do you deduce that n equals m there? That is not straightforward. If it is differentiable, so if you have a diffeomorphism, that's basically a linear algebraic problem. It's not that complicated, relatively. Compared to the invariance of domain. Or maybe I'm not that comfortable with invariance of domain. I don't deal with topology that much, but yeah, maybe we can discuss this later. I don't have a lot of intelligent things to say about this. Okay. So somehow topology is, this context of topology, the topological category is rather malleable. It's not as malleable as sort of the measurable category, which I'm more comfortable with, but somehow the measurable category is, I don't know, you can do more analysis with it, I guess, so I feel more comfortable with that. Okay, so Minkowski dimension. Before that, let me say, now we're studying analytical dimension theory. Yeah, I'd like to discuss Minkowski dimension. Certainly, we're going to discuss Hausdorff dimension. Maybe if you have time, or maybe I'll write something in the notes about this. It turns out that you can, in a sense, interpolate these two notions of dimension, and these are what Falconer calls intermediate dimensions. So maybe I should write it. Well, let's just write it like this. Then there are certain versions of Minkowski dimension that sort of like give different notions, modified Minkowski or packing dimensions, and so on. And ultimately, the main idea there in all of these pretty much is that not only do you want a notion of dimension but also a notion of size. So here's what I mean. Pretty much with all of these, to all of these, there is associated some notion of a measure. It's not always true. For instance, in the case of this, vanilla Minkowski business, but for instance, for the Hausdorff dimension, which is sort of like the prime example of this theory, there is what is called the Hausdorff measure, which we're going to discuss. And so what is the difference between sort of like a dimension-like thing and a measure-like thing? So maybe I should write that over here. So to dimension 1, the corresponding notion of measure should be something like length. And of course, if it is 2, the corresponding notion of measure should be area. And then if it is 3, for instance, it would be volume. And it goes on like this. So you see, this notion of a dimension and the notion of size or measure are somewhat intimately related to each other, but they are not exactly the same thing. And somehow their connection, once you sort of like establish some sort of connection between the first row and the second row, so let's say alpha measure and them being equal to alpha, it turns out that you can sort of like generalize this correspondence to fractional values. These are sort of like general statements. Let's switch back to Minkowski dimension so that we have something more concrete to think about. In a sense, Minkowski dimension is a light version of Hausdorff dimension. Hausdorff dimension takes some work. It takes some work to establish Hausdorff dimension. And the heuristic behind this Minkowski dimension is the following. You have a subset in some metric space. So this is the heuristic. This is one of the heuristics. There's another heuristic that I might mention in a second. You have a subset in a metric space. And you cover it using small pixels. The heuristic is that the number of so you should have sort of like an equation, which is that the number of pixels times the size of the pixels to the dimension should be a constant. So scales of pixels, or scale of pixels. Constant in either one of these numbers, because somehow it's reasonable to expect that the scale of the pixels should be related to the number of pixels and vice versa. Any questions about this?
Could you like map it to a like R2 or some other physical thing?
Yeah. I'm going to give an example.
I have a question. Are these all going to be like topological notions?
No, they're all analytical. Yeah. So you see, in the context of the Lebesgue-covering dimension, it was more sort of like almost combinatorial. And in fact, I was going to discuss this sort of like more combinatorial underpinnings of Lebesgue covering dimension, but I decided not to. One thing you can do is, given any cover, you can associate to a space a certain combinatorial object, which is called a, a topologist would call it a simplicial complex. It's called the nerve complex of a cover. I was going to get to that, but I decided not to because we're not going to use it. Okay, so of course the first example is the interval inside the real line. Now I'm not even saying anything about what sort of pixel. Is it open, closed, is it a ball, whatever. Now there's a couple definitions of Minkowski dimension that turn out to be equivalent, but let's just try to understand this heuristic. If my pixel size was, let's say, 1 over n, so size, well, I would need approximately n pixels, okay? Because you see, what do I mean by scale? Do I mean the diameter? Like, what do I mean? It doesn't really matter. So this is sort of like the nice thing about Minkowski dimension, and many of these more analytical notions sort of like have this property too. Because eventually I'm sort of really interested in the asymptotics of this equation as the scale goes to 0. I don't care that much about some constants. So the number, let's say, is n. So one specific thing would be something like this, right? So interpret the scale as diameter. So I want to cover the interval using a bunch of sets of diameter 1 over n. I might as well use, let's say, closed intervals. Well, one thing I can do is I can take these 1 over n, 2 over n, 3 over n, and so on. So n minus 1 over n, and then 1. Okay. So how many are there? Right, so I have n many. This is the first. It's a closed interval. Diameter is 1 over n. Then this is the second, and so on. And then depending on the even or oddness or oddity of the n, this is going to be either yellow or red. But in any event, I have n many. Okay? And of course, n times 1 over n to the 1 equals constant. In this case, it is exactly 1. Okay? Let's try to be more specific about this. I'm going to take really n to 0. Sorry, n to infinity. As I take n to infinity, the scale goes to 0. And really, when you think about it, I want something like this. Find the number d such that this expression doesn't blow up as n goes to infinity. So right? So calculus says that this is basically the same thing. So I don't need to take integer values. I can take real values. It's the same limit. Or rather, whether or not this limit blows up has nothing to do with the integer values and so on. So this is nothing but limit as x goes to infinity of x divided by x to the e. And then if you want L'Hopital or whatever, the only way this is bounded is when the denominator grows as fast as the numerator. In this case, d has to be 1. Okay, this is the intuition. Any questions about this? And you see, the same intuition works in higher dimensions as well. That if I were to take sort of like a rectangle in 2 dimensions, for instance, well, you see, this time, again, I want to say something like this, right? Scale. Let's do this in 2 different ways, actually. Now, what do I mean by scale? I can again mean the diameter, which would mean the length of the main diagonal. Let's take that. It's not going to matter how I really count this, insofar as I'm doing sort of reasonable things. If I'm counting as the scale, the diameter, oh, maybe I should do something like this. Let's say that the scale is root 2 over n, so that the diameter comes out easy. Right, so because if this is like a small pixel and it's a square, if 2 sides are 1 over n, then the diagonal is going to be root 2 over n, which is going to be the diameter. Okay? So if I'm interpreting the scale in the sense of diameter, then the number of pixels should be what? How many of these little boxes do I need to cover the whole A? N squared. Okay, so based on this heuristic, I should have something like this. N squared times the scale to some dimension should be constant. Let's call it C. You leave that constant as is, because you're really worried about this power law. You're not really worried about that constant, what the exact value is. Okay, so how do you solve for D? Again, you can use the same argument here and say, oh, I want really this to not blow up, and the only way this can happen is if this grows the same way as this grows, and that can only happen if D is equal to 2. You can do this. Or you can sort of try to do more algebra. And so how do you solve this for D? Well, you take the log. So you have 2 log n plus D log root 2 plus, oh, let's leave it like that actually. Divided by n equals log C. Okay, solving for D gives this. So send this to the other side. And then divide by this. Okay? So the constants don't matter, basically, because you're going to take n to infinity. These don't matter. This cancels out with this, and you have 2. Okay? So in a second, I'm going to give the actual definition of Minkowski dimension, or upper and lower. But when you see it, you're going to see an expression of the form log of something divided by log of something else. And it really comes from this, okay? Now, if you keep track of how we came up with this thing, really you should think of it like this. D equals log of the number here. In this case, it was n squared, and there's a minus here, but that's going to cancel out with this. Don't worry about that. You should think of D, Minkowski dimension, basically as log of this number divided by log of this number. So that's another heuristic. Any questions so far?
So
Yes.
is the intuition for choosing the scale sort of problem dependent on what
Yes.
space you're looking at?
Yeah, exactly. Yeah, in fact, if you were to try to compute the Minkowski dimension of, let's say, the Cantor set using this intuition, it's going to give you the upper similarity dimension. Let's do that too, actually. Oh, even before that, let me say this. Or maybe instead of interpreting this notion of scale in this heuristic as the diameter, maybe I take it as the side of one of these boxes. It would give you the same thing, right? Because that number, this root 2, goes here, and when I take the limit, it's not going to say anything. It's not going to affect the end result. So somehow it is more analytical, so you need to do some sort of calculus and stuff. But in a sense, it doesn't depend on certain numbers, certain choices you're making when trying to compute it. So let's say that C is the middle thirds Cantor set. So again, I want to come up with a heuristic like this. I need a scale, and I need a number. Okay. So how did we construct this? We have this interval. I mean, we can use this iterated function system in business, but let's try to not use technology. So in one step, we shrunk whatever is remaining by 1/3. And we have two of them. Okay? So at step n, you're going to have 2 to the n disjoint closed intervals, each of which has length 1/3 to the n. I mean, many of you know this because you looked into these type of things in previous reports. So this suggests that the scale should be 1/3 to the n, and the number should be 2 to the n. Okay? So if I were to take this and put it into that formula, I get this. So this has to stay, I think. So it's either this or it's reciprocal. So ultimately, so this gives me log 2 over minus log 3, which is correct, which is false, which means that I should take really 3 over.
Are you just missing that it should be a negative for, I think the definition is just a negative, and then when you flip the...
Yeah.
Okay.
Yeah, so here I should put a minus, so to the -1. Or, minus here. Yeah. Okay. So whenever you have sort of like a new notion of dimension, the first thing you should do is you should compute a couple of simple examples so that you know what that dimension should give as numbers to these obvious sets. And then you can figure out the sort of like the details of the notion. And of course, if I were to, n's cancel out here and I get log 2 over log 3, which is the upper similarity dimension. It's the same thing. Okay?
So does the n represent the nth step of the Cantor set here, or is it?
It might represent that, or it might represent the scale. Okay? Because, so you want to think of it like you're trying to express it in a computer. Like from a mathematical point of view, we define the Cantor set as that limit. But from a computational point of view, whatever your scale is, you're not going to see the Cantor set as this totally disconnected thing. Right? That's the point. Okay. Any other questions? And so now, the way you formalize this notion of a Minkowski dimension then goes through formalizing the relationship between scale and the number of pixels. And so there are multiple ways of doing this, but let's just focus on one of them. This is not exactly what Barnsley does, but this I think is rather easier to define. Let A be a subset of a metric space. I'm going to fix an epsilon. What I'm going to say in a second is not going to work, but we're going to sort of change it a little bit. Let's define this number. The epsilon-covering number is, I'm going to note this like this, n sub epsilon of A is going to be the minimum of all numbers, integers. So the number of elements in curly C, where curly C is a collection of subsets. Recall that P of x was the power set, so the collection of all subsets of x. I want the diameter of each cell in this cover C to be bounded by epsilon. So that's my notion of scale. And if I were to take the union of all the cells in C, I want that union to be a superset of A. Okay. Now this doesn't necessarily give you an integer, but if I were to take a totally bounded subset, then this is indeed an integer. Okay, so that's an exercise. It's a number that is at least 0 and is an integer. Okay. So let's try to understand this number using sort of the interval, for instance. So I'm saying I want to cover A using cells of each of which has a diameter at most epsilon. So intervals I might choose. So you see, this definition allows you to take any cover whatsoever. You can take like crazy sets to cover things. But here I have sort of a nice candidate. And because ultimately I'm going to take the min over all such things, at least this is going to give me an upper bound. So the C is 0 to 1 over n, and then 1 over n to 2 over n, and then 2 over n to 3 over n, and then n minus 1 over n, and then n over n. You see, curly C is a collection of subsets of X, which is the reals. Clearly, it has exactly n elements. So number of C equals n. But since this number is bounded from below by that number, this must be the case. Okay. How about the lower bound? Well, that's the harder part, of course, and I'm going to leave that as an exercise. It is true. It is true, though. So how can you do this? Well, you're going to take any curly C whatsoever, such that the diameter of any cell in C is at most 1 over n. That covers the whole interval. Oh, it's not that hard, actually. Okay, yeah. This is a nice thing. So show, this is a nice exercise. Any C, collection of subsets. So let's write it like this. C1, C2, dot, dot, dot. It doesn't need to be countable necessarily, such that the diameter of each of these cells is at most 1 over n, and then if I were to take the union of them, I get the interval. Then I have to have at least n cells in here. The ultimate idea here is that you can say something like this. Okay, this, if I were to take the unions of all the cells in C, that's going to cover the interval, which means that there's at least one cell in the collection that covers 0. If it covers 0, and if its diameter is at most 1 over n, it cannot cover any other number larger than 1 over n. Okay, so I need to have another element and so on. So that's how you generate extra cells. Okay, this is a very nice exercise, actually. Okay, any questions about this? Now, once you define this, all you need to do is to plug this expression into the heuristic and look at the limits. I'm going to do it over here. Consider the limit of log of the number of things, log of n sub epsilon of A, divided by minus log of epsilon, or log of 1 over epsilon, same thing, as epsilon goes to 0. Now, this limit may exist, may not exist, but if a limit doesn't exist, you can always look at the maximum accumulation point and the minimum accumulation point. That is to say, you can look at the lim sup and lim inf of this expression. And so those give you the upper and lower Minkowski dimensions. Let me just write the names of these. So when you take the lim sup of this expression, when epsilon goes to 0, you get the upper Minkowski dimension. This lim sup always exists. Possibly infinite, but always exists. And this lim inf too always exists, and this is the lower Minkowski. Dimension. So we have two new notions of dimension for a subset. Questions?
Is there a not terribly hard example of a set that has a differing Minkowski dimension to its covering?
Yes. I mean, it would take some time to do this, but we're going to look at some examples of computation of this that are slightly more complicated than the examples that we looked at before. But yeah.
What's the significance of, I mean, is the upper and lower specifically for tailoring it into a certain dimension, or is it?
It just gives you two things that are well defined. No matter what A is, this is a well defined.
Is there some different notation for the epsilon going down, like the limit being down a bit narrow, or is that just?
I mean, yeah, I guess here I also mean that limit from the right. I want decreasing epsilons. I never take epsilons to be negative. You can take epsilon, horizontal arrow 0 too, if you want it. Any other questions? Okay, let's take a 5-minute break. When we get back, we're going to continue. Okay, I think we're all back. Let's continue. Okay, welcome back. So by definition, whenever you take a quantity, and as you're taking the limit, you look at the lim sup and lim inf. Well, the lim inf is, syntactically speaking, has to be bounded from above by the lim sup. So that's by definition. If these two values coincide, then you just denote it by dim sub m of A, and it's called the Minkowski dimension of A. Now I should also mention there are a couple different names for this. Upper and lower as well, if you want it. So the name is Minkowski-Bouligand, Bouligand, I guess. And then box. We're going to say, I want to say something about why it's called a box dimension, or it's called a fractal dimension by Mandelbrot and Barnsley as well. I should also mention perhaps that Lebesgue covering dimension is also called Lebesgue check covering dimension and so on. So typically one of these people sort of like formalize an idea and then someone else sort of contributes, makes like major contributions, and then they start adding names. Okay. Let's try to compute some things. Oh, I should just mention this. There are examples of sets of the interval, even subsets of the interval, whose lower and upper Minkowski dimension are separate. They're not the same. But it takes a while to describe it, and I don't exactly remember it. And it takes some computation to show this as well. But let me just mention that in Pessin and Klemenhager's book, there's a nice construction. So let's write it like this. Proposition. For any two numbers, lambda and rho, let's say, strictly between 0 and 1, let's say that lambda left is less than the one on the right, rho. Then there is a subset, A sub lambda comma rho. That's an explicit construction. Such that its lower Minkowski dimension is lambda and the upper Minkowski dimension is rho. So that means that I'm not going to prove this because it's somewhat finicky. But this would be a very nice sort of thing to study for a weekly report, probably. That means that in the general setting, the value of the lower dimension and the upper dimension, they are basically independent variables. They're independent from each other. Now, in different situations, if you have some more assumptions, of course, you might get that they're the same number, and that's sort of the context of, for instance, this Moran-Hutchinson formula. In the context of the Moran-Hutchinson formula, you have that if you have a B-IFS acting on some Euclidean space by similitudes, like the Cantor set construction or the Sierpinski construction and so on, and if you have this open set condition, it's this separation condition, then in fact, these two numbers are the same. So the lower Minkowski equals to the upper Minkowski, and they equal, in fact, to the upper similarity dimension. Okay, so that's sort of where we're heading toward. Okay, so here's an example. Let's look at this. I want to look at sort of an exponential progression. Let's say 1 over 2 to the n and non-negative integer. Now, if you want, so this is not compact, for instance, it doesn't have 0. But if you wanted, you could have added, the 0 point. It's not that important, of course. But the point is that this is a subset of the interval. Let's try to compute its dimension. So the points in this set A are these. Okay, 1 is there, and then 1/2 is there, and then 1/4 is there, and so on. Okay. Any guesses as to what the dimension should be? So you want to go back to that heuristic formula. Log of number of pixels divided by log of 1 over scale.
Trying to do it, visualize it in my head. It's just you use n. Can you use n coverings of length 1 over 2n, or is it?
ultimately that should be the point, right? Like the point should be that if you fix your scale at an exponential rate, well, you should need only finite many of these. And the point here is that, let's say this is, so this somewhere here is 1 over 2 to the n. If you were to look at the closed interval, let's say, of diameter 1 over 2 to the n, whose center is here, you're going to cover everything to the left. But you won't be able to cover any of these. Okay? So that means that approximately, so you're going to be able to cover this whole thing, but then no others. So for each of the remainder, more separated ones, you're going to need 1 plus 1 pixel. So that means that you need, so if this is the 1 over 2 to the nth one, how many more are there here? Approximately there are n many. Okay, so the number should be n then. Okay. So log of n divided by log of 1 over epsilon is log of 2 to the n. I'm going to take n to infinity. Okay, log of n, it grows, but it never grows as fast as n, which means that as you take n to infinity, this is going to go to 0. Now this is sort of an upper bound, but if the upper bound is 0, everything is 0. Okay? Now the exercise is to make this formal. So really, you should sort of take this set or that set and try to sort of, draw some pictures and so on. And you should be able to come up with some numbers, at least bounds, without using too much sort of like formulas mode. This is the n epsilon covering and all that stuff. Okay? You should be able to do that too, of course, but the point of the Minkowski dimension, or why it was popular, it's still popular today, is that it's rather easy to estimate. And it's also easy to handle using computers. Any questions? And I believe that the same argument, if you think of it the other way around, gives you that its Lebesgue dimension is 0. It's always good to compare, just to sort of develop some intuition. Because ultimately, I was able to come up with an open cover such that no two cell and open cover intersect. That's the idea. Okay, so in this case, it turns out that the Minkowski dimension is the same thing as the Lebesgue dimension. Okay, it can happen. Any questions? Yes.
In this example, it seems like you could say the dimension is the degree of the order of any epsilon cover. Does that extend for like Minkowski?
What do you mean by degree of an order?
So if I have a 1 over n cover, then I need order 1 in this case, or order 0, I need just a constant number of covers, and then if it were like a square, I'd need n covers. Does that make sense what I'm saying?
No. Sorry.
Oh, that's got it.
Yeah. I mean, it's probably true. Okay. So let's try to come up with an example where the Lebesgue dimension is not the same thing as the Minkowski dimension. So the conclusion of this whole thing is that the Minkowski dimension of A is 0. Okay. Now, how can we come up with an example? And this also gives some idea as to how we can come up with an A sub lambda rho like this as well. Now, ultimately, the reason why we can do this is that the scale is 1 over 2 to the n, and the number is n. And the reason why that happens is that ultimately this sequence converges too fast. It converges at an exponential rate. Now, if I were to slow down that exponential rate to polynomial, it is hopeful to think that, oh, maybe the Minkowski dimension is going to be something positive. Okay, some number, some positive number. And okay, let's try to think of that example. And then basically an adaptation of the same idea gives you this. So I'm going to take a polynomial sequence this time. And of course, perhaps this is straightforward, but if I were to take any alpha that is larger than 1 instead of 2, the whole calculation would follow through. It would give you the same thing. So let's look at this. 1 over n. So you see, this is a polynomially converging sequence. It's not as fast as that guy. Any guesses as to what the dimension of this is? You sort of did a similar example, but you overcounted.
Did I ever count?
Yes, yes. What you gave was an upper bound. Okay. It turns out that your upper bound is exactly the Minkowski dimension of this guy, actually. So it's 1 over 2, but we're going to see. So I have this point, and then 1 over 2. And then you see, instead of going to 1 over 4, you stay a little bit farther, 1 over 3, and then 1 over 4. Again, these points accumulate to 0, but it accumulates in a slower fashion. Ultimately, the idea should be the same when we're trying to come up with this scale versus number business. That if you were to take an interval centered at one of these points that are near the origin, near the 0, you should be able to cover everything to the left of it, and then you want to count the remainder. Okay, that's the idea. So instead of using an exponential scale this time, seems reasonable to use a polynomial scale. So let's say that I'm trying to cover this using sets whose diameters is bounded, is 1 over n. Okay, so let's say that my guy is over here. At the nth step, I'm here. If I were to take, maybe let's do 2 over n perhaps. Yeah. If I were to take the closed interval centered at 1 over n, whose diameter is 2 over n, that is to say, radius is 1 over n, I would cover everything to the left. Okay? Cover everything to the left. Now you want to count how many you're missing, but you want sort of like a nice bound, nice number here. So let's zoom in on this. What is the one before? It is 1 over n minus 1. It's a larger number. And so what is this difference? Right? Because you're trying to figure out if this point is inside the 1 over n ball centered at 1 over n. So that is to say, you're trying to compare this distance to 1 over n. I'm not going to do this calculation, but compare 1 over n to this distance. Okay, you need to do some calculus here. You need to do some comparisons. But ultimately, this shows, it turns out, that the Minkowski dimension is 1 over 2. Okay, it's a very nice exercise. I highly recommend it. And more generally, if I were to take if I were to take a faster sequence, I would get something like this. Um, 1 over n to the m becomes 1 over m plus 1. So if I were to look at 1 over 1 and then 1 over 4, 1 over 9 and so on, that set would have dimension 1 over 3. Yes?
To answer my earlier question by example, is the 1/2 because we need log base 2 elements in the cover?
No. It has, no. Any other questions? Now, there are a couple different alternative definitions of Minkowski dimension. Let me give 2 of them. Because each of these different definitions sort of like really is related to a different intuition. Okay, exercise. In the definition of lower Minkowski, upper Minkowski, one can take, instead of an epsilon of A, this number of coverings, you can take, okay, what is it called? Okay, I don't remember the names now. But here is an alternative. This is more along the lines of this total boundedness property. Number of elements in a subset that covers A. Oh, okay. This is called spanning in the context of dynamics, or nets in the context of general topology. So I'm trying to say here that taking the minimum number of centers or points in A, such that if I were to take the union of all the epsilon balls around it, around those points, I get to cover the whole A, or max of the number of points in A, such that any 2 points that are distinct in F is separated by epsilon. Okay, so this is sort of like a packing number, if you want, epsilon packing number. This is epsilon net number, or epsilon entropy number, some would say. Now, I'm not saying that this number is the same thing as this number, which is the same thing as this number. I'm not saying that. I'm saying that the limit is going to be the same. Okay, so that's sort of slightly tricky. Okay, any questions? We didn't get why it is also called box dimension. but on Thursday we will. Thank you. Let's start. Good afternoon. So today I'd like to say more things about Minkowski dimension. Mention this second heuristic I kind of mentioned a little bit. At the very least, I declared that there's a second heuristic that would lead to a notion of Minkowski dimension. I want to discuss that because it's also very useful, I think. And I'd like to look at some more examples, some more calculations. And if we have enough time, oh yeah, I want to relate Minkowski dimension to Lebesgue dimension. And if we have enough time, I want to start discussing Hausdorff dimension as well. And then next week, we're going to spend basically the two classes proving at least some version of this Moran-Hutchinson formula. So before that, here's an exercise. So if I have a B-IFS with unique attractor A sub W, I'm declaring this trivial case. When you're reading this stuff, typically people assume that you have at least two functions that are non-constant and stuff like that. Ultimately, because we're going to try to relate this upper similarity dimension to some other dimensions, right? And when you're trying to define this upper similarity dimension, well, you're looking at this equation. But in order for this to make sense, really, so far we didn't say this, but we were thinking of all of these as non-constant. Because if, let's say, W2 is a constant function, certainly it's a contraction, right? Let's say that that's the fixed point. And so the Lipschitz constant of this, which is going to get into this, or we're going to plug in as AI, is going to be 0. And when you're doing this, when you're writing this left-hand side, you don't really write 0 to the t, right? Because then you're going to have to say what is 0 to the 0 and stuff like that. You really sort of sum over all Lipschitz constants of functions that are not constant. And so if you had at most one non-constant function, so either all functions are constant, in which case you have a finite set, of course, or you have one non-constant function and the rest are constants, well, that means that we have, let's say, non-constant else constant. Well, this would give you something like this, right? So I'm just going to have a1 to the t equals 1. And I guess because this is a positive number, the only solution to this is t equals 0. Well, I guess in that case, it actually works too. But our methods are not going to work necessarily. So this you can compute rather straightforwardly in this situation. I'm saying that if you have at most one non-constant function, the attractor is going to be the fixed point, and the orbits of the fixed points of the other guys under the non-constant function. And you can straightforwardly compute that the Lebesgue dimension is 0 and the Minkowski dimension is 0. Here's a nice exercise too. This is what is called finite stability of upper Minkowski dimension. That if you were to take the union of two sets and look at the upper Minkowski dimension, it's equal to the max of the upper Minkowski dimensions of the pieces. One of the reasons why Minkowski dimension is not as nice as Hausdorff dimension, at least from a technical point of view, is that you cannot do this with infinitely many sets. Because we saw an example I gave as an exercise. So for instance, 1 over n, and starting from 1, this was a set that we looked at last time. So this has Minkowski dimension 1 over 2. But of course, this is the countable union of singletons, each of which has Minkowski dimension 0. You see, this property doesn't really hold for infinitely many sets, but for finitely many, it does hold. In the case of Hausdorff dimension, it's going to hold for infinitely many as well. Okay. So the second heuristic for Minkowski dimension. And this is also related to why often people call this box dimension. And for this, we're going to restrict ourselves to the situation where the metric space is the nice metric space, which is the Euclidean space. Let's call it RD. Okay. So let me look at this. Let me fix a number that is less than D, let's say M. So well, let's say like this, 1 or D minus 1, 1 to D minus 1. So that I can think of RD as Rm times Rd minus M. Let me take a small ball here, okay? So, so one way to write this would be something like this. So I'm going to define my set A, it's going to be a subset of X. Let me define it like this. The unit ball in m dimensions times, in the second dimension, I'm saying it's 0. So maybe I should write it like this. X. So you should think of it like this. So for instance, here, let's say D equals 3, and then M equals 1. And let's say that R1 is this piece. So my A is going to be just a line segment. Okay? If I had D equals 3 and M equals 2, then I'm going to take a ball in 2 dimensions. Okay, so it's going to be this thing. So it's going to be a 2D thing. So this heuristic is about detecting that the dimension of this guy, even though it's a subset of this larger dimensional thing, should be M. Okay, that's sort of, you're trying to calibrate your understanding of dimension this way. So what you do is you look at the doodle of this set. Okay, so that is to say, you want to look at an epsilon ball centered at A. Okay, so look at the epsilon doodle of A in RD, in the larger space. So if you were to look at the epsilon ball of this line segment, what type of a shape do you get relative to the standard Euclidean metric? So, so this doodle is, in our notation, this. In other words, it's the union of all balls, d-dimensional balls, whose centers are in A. So what is this shape if I'm in this situation? What is the doodle? What type of a shape should I be getting?
Rounded cylinder.
Yeah, it's like a pill, right? So when you take the doodle of this, you're looking at the union of all balls of the same radius, epsilon, whose centers are in this interval. Okay, so you're going to take a three-dimensional ball, and you're going to sort of move it around. And when you sort of like move it this way, you get this pill shape. Okay. Okay. So this is now a three-dimensional shape, and this is going to have a a d-dimensional volume. Now, if I were to look at the volume of this A, okay, so d-dimensional volume of A, it would be 0 because, you know, intuitively it has less dimensions. But this is going to have dimension d. So you want to bound, you want to come up with upper and lower bounds for the d-dimensional volume of this. So d-dimensional volume of A is 0, but the d-dimensional volume of its doodle is some number. Okay. Some positive number. So d-dimensional volume of the doodle of A is positive. So you want to bound this number. So let's think about this. So let's consider the case d equals 2 and then m equals 1. Basically this situation, but in one dimension less. So I'm looking at this situation. Here's my A. And then when I take the doodle of it, I get this thing. Okay. So what is the volume of this? So this is delta, or epsilon in this case. Now, first of all, here's an upper bound, for instance. And I know that this length is 1. This too is 1. Well, the blue shape, the pill, is going to be included in, let's say, in the product of two balls of smaller dimension. Let's say epsilon, I'm going to take it to 0. Let's say that epsilon is less than 1. Okay. If epsilon is less than 1, then that means that this doodle can be included in the following. So maybe I should be more explicit here. This is a ball in d dimensions. So this should be included in A less than epsilon r m times, well, in the remaining coordinates, in these coordinates, I don't have any thickness, which means that this should be here, d minus m 0 epsilon. Okay. So basically, this inclusion just says the following. This pill is included. It's included in the box. That's what I'm saying. And consequently, of course, the volume of the doodle should be bounded by the volume of this guy. The point is, it's relatively easier to compute the volume of the larger one. I want to do the same thing with the with a lower bound. Well, note that okay, and here's a smaller box that I can put inside. This smaller box, the green box, is included in the doodle, and so I have the following. So how can I write that? Well, that's just going to be I just have the base guy. So A times the ball in the complementary dimension of radius epsilon. Okay. So this represents the smaller green ball. Okay. Now I'm going to take epsilon to 0. And epsilon is less than 1, which means that I can replace this epsilon by 1. And that's still true. So that means that the volume of the doodle is bounded from above by the volume of this. And because it's a product set, it's easier to compute the volume of this. And likewise here. So volume of A, so I'm computing the volume of this thing. Oh, sorry. So maybe I want something different. Give me a second. Lower. No, it's okay. It's okay. This is the m-dimensional volume. Okay, so I'm trying to compute the volume of this product. The volume of this, the d-dimensional volume of this product, is the m-dimensional volume of A times the d minus m-dimensional volume of the ball. Well, we know that the d minus m-dimensional volume of an epsilon ball should be some number times epsilon to the d minus m. Some number times epsilon to the d minus m. So that's the lower bound. Then I have this d-dimensional volume of the doodle then this is bounded by the m-dimensional volume of this times the d minus m-dimensional volume of this. Well, this is going to be a some number that I don't really care that much about. So let me denote it by C2. And then this is going to be, again, you see, epsilon to the d minus m. And in fact, let me also let this constant absorb this constant to get rid of this, so that now I have this expression, these lower and upper bounds. Okay, so I have that the volume of the doodle is proportional to epsilon to the d minus m. So let me write it again. Okay. So the point, so what we're trying to do is to somehow solve all this for m. We want to take some limit and so on, and ultimately we want to end up with m. Okay, so what can we do here? Okay, I can take the logs. Okay, divide everything by log epsilon. Let me not keep writing this. So now I have log epsilon here, log epsilon here, and then this goes away, and then a log epsilon here. Okay, so now if I take epsilon to 0, okay, so the numerator is some constant that doesn't depend on epsilon. It might depend on dimensions and stuff like that, but it certainly doesn't depend on epsilon. which means that as I take epsilon to 0, log of epsilon is going to go to negative infinity, which means that this is going to go to 0. And likewise, this too is going to go to 0. Which means that by, squeeze theorem or whatever, the limit as epsilon goes to 0 of this expression equals d minus m. Solving for m, I have that m equals d minus this limit. Okay? So that means that if you're trying to compute the true dimension of a subset in d-dimensional space, what you can do is you can take the subset, thicken it a little bit, right? Take the doodle of it so that it has now some copy, some version of it that has positive d-dimensional volume, and then take this limit to 0. Whatever number you get is going to be what is called the codimension. So this limit is going to be d minus m. So if you were to subtract that number from the top dimension, total dimension, you're going to get the true dimension. So this is the second heuristic. Any questions about this? Maybe I was a little bit shady in these calculations, but it's good to do these on your own as well. And so what you do is the following then. Now it's an exercise. For A bounded, its Minkowski dimension, or upper and lower Minkowski dimension, is equal to this expression with the lim sup or lim if. Similarly for let me just write it like this. Okay. Now, here's a question. What if A is not bounded? Let's say I'm trying to compute the Minkowski dimension of RD itself. You can use any definition whatsoever, but you're going to realize that if you try to use any one of these definitions, Minkowski dimension is going to turn out to be infinity. So you see, now you've calibrated the definition so that it works for bounded sets, or totally bounded sets in general metric spaces. But now it's not working well with, in a sense, nicer sets, at least from an algebraic point of view. So the way you remedy this is by realizing the following. If I have two subsets, one nested within each other, then the upper Minkowski dimension of the smaller one is not larger than the upper Minkowski of the larger one, and vice versa and likewise for lower Minkowski. Based on this, you just say, okay, so if I'm trying to compute the Minkowski dimension of Rd itself, what I'm going to do is I'm going to take a nested sequence of balls or sets that have finite Minkowski dimension, and I'm going to take that limit in a sense. So X metric space define the upper Minkowski dimension as, well, the upper Minkowski dimension of A, if you want to take a soup, you want to take the soup of all A's, A totally bounded. Same with lower Minkowski dimension. And if you use this definition, here's an exercise that no matter which definition you use, the Minkowski dimension of Rd is going to be equal to D. So this somehow calibrates properly the notion of dimension. Okay. Questions? Nice. So now let me say a couple words about why people call this box dimension as well. Again, this is typically in the context of Euclidean spaces, or bounded subset of Rd. But I think I have an idea as to how to generalize this to arbitrary metric spaces. It might be janky, but I'm going to mention it and give it as an exercise to see if it works actually. So, let me say why. So let me also mention that this intuition that I'm erasing here is also why this is called the Minkowski dimension, because this idea is ultimately related to something called Minkowski content. It's not exactly a measure, but it's something like a measure. That's what's called a content. So Minkowski was looking into these things, and then people realized, box dimension is the same thing as this other dimension that you can get by basically using Minkowski content type ideas. Okay. Okay. Exercise. I'm going to take a bounded subset. Let me look at this. I'm going to take an epsilon. And I'm going to look at what is called the epsilon-mesh in Rd. So, and an easy way to denote this is to write it as epsilon times z to the d. So what do I mean by this? I just mean the subset in Rd here consisting of epsilon scaled versions of tuples of integers. So epsilon n1, epsilon n2, dot, 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 epsilon nd, such that ni is an integer. So this is an epsilon scaled version of the integer lattice, if you want. Now the exercise is that if you were to use, instead of the standard n epsilon of A definition and the definition of Minkowski dimension, if you were to use the following, so this is the next alternative. This equals number of A intersect the epsilon mesh. So the exercise is to show that you can use this and epsilon in the definition of Minkowski dimension. And you see, this is basically this idea that you have this subset in Euclidean space, and you have these small pixels. Now I'm literally thinking about pixels, and I'm looking at the number of small boxes that hit A. Okay, and I'm counting that. And then how do you compute the Minkowski dimension? Take the log of that number, divide it by log of 1 over epsilon, and then take epsilon to 0. Whatever that number approaches to should be your Minkowski dimension. Okay. Now, here's an exercise. It's my attempt to generalize this idea to arbitrary metric spaces. Or perhaps even before that, let me give you one exercise. In a sense, this epsilon-mesh in RD, this epsilon ZD, converges to RD. How can one make sense of that? Well, we have one sense of convergence for sets. It's the Hausdorff convergence. But that's for compact subsets, and neither RD nor epsilon ZD is for compact, neither of them are compact subsets. But it turns out that you can literally use Pontryagin-Schrinelmann distance for closed non-empty subsets, and it still works. And we could have sort of developed a whole theory for closed non-empty subsets if you wanted, but it's slightly more cumbersome, so we didn't do that. But so here's an exercise. So this is a new hyperspace. Let's call it f of x. Closed non-empty subsets. Certainly it contains the non-empty compact subsets. So this hyperspace that we were using is a certain subspace of this. And it turns out that x is complete if and only if this is complete, blah, blah, blah. You have all that stuff. F of x complete, etc. And so if I were to, and epsilon ZD and RD are both non-empty closed subsets of RD. And of course, I'm thinking about the Pontryagin-Schrinelmann distance on this space again. And so that's an exercise. Again, I'm going to denote it like this. Pontryagin-Schrinelmann, epsilon ZD and RD. Well, limit as epsilon goes to 0. Or maybe let's write it like this. Limit as n goes to infinity, dh of 1 over n ZD, comma RD is 0. Okay? And so based on this, here's an attempt to generalize this box dimension, or this characterization of Minkowski dimension using boxes to arbitrary metric spaces. What I need to do is something like this. So first of all, I need to have sort of like a subset or a sequence of subsets that converges to the whole space. That's one thing. But furthermore, there's a certain homogeneity to this mesh, right? Because it is made up of boxes of same size. and same shape. So how do you sort of formalize that? Well, you need to use what is called an isometry or isometry group. And so you can think of it like this. So I can think of, epsilon ZD as a certain group of isometries of RD, as a subgroup of the group of isometries of RD. What is the action? So I'm saying that I can think of any epsilon times two integer tuples, any tuple like that, I can think of it as an isometry. So it's a homeomorphism that preserves distances. Well, it's just going to be translation. Right? So I can say epsilon 1, 1, for instance, when d equals 2, it just means translate everything by epsilon unit to the right and epsilon unit upwards. Okay? So I need to have a family of groups like this as well. And then what is the subset? So if I were to think of it as a subset, it's really the orbit of this group. So exercise. X arbitrary metric. Say there's a sequence of isometric groups. Okay, I need to say something, of course. Say there is a sequence Gn which has no finite index subgroups. This is like a technical condition. And say there is a point x star such that the Gn orbit of x star converges to x. So let me continue here. There's an x star such that limit as n goes to infinity relative to the Pompei-Hausdorff distance of the orbit of x star relative to the Gn action converges to the whole space. Define n sub n for A. Totally bounded. Define this number, let's call it, well, relative to this G guy. Well, I'm just going to define it to be the number of the intersections of A and this. So in a sense, I'm sort of redefining this more static notion using, if you want, hitting times. So this is sort of like a bizarre thing to think about, but I can think of this as a dynamical system itself. For each n, I have a different dynamical system, and somehow, as n goes to infinity, this dynamical system moves things less and less, lesser and lesser. And I'm claiming that if I were to use this, I'm hoping, if I were to use this, I would get the same thing as the Minkowski dimension. Then is it true that one can replace n 1 over epsilon A in the definition, 1 over n in the definition of Minkowski dimension by this? Certainly you can in this case. In this case, you can do it. In the Euclidean case, it works, but in general, I don't know. It's a nice exercise. Okay. And this condition basically tells me that this dynamical system sort of like is infinite in a sense. You're not returning in finite time. Because if you think about sort of these translations, so if you're translating, it's like you're never returning unless you're actually trying to return. So there's no sort of coincidental sort of cyclicity going on. Okay. Any questions about any of this? Okay. So here are two things. So we talked about how Lebesgue covering dimension is an invariant of homeomorphisms. So it's a topological invariance. Minkowski dimension is not a topological invariant, but with Hölder functions or Lipschitz functions, it works really well. Okay. So here's what I mean by this. And this is going to be a property that Hausdorff dimension 2 has. Remember, when we were first talking about Hölder property or Lipschitz property, I told you that these are basically differentiability properties. And indeed, these more analytical notions of dimension are more in this context of differentiability, really. Somehow, if you have a metric space that is arbitrary, you can still get away with things a little bit, but that's sort of a good way to think about it. So here's a proposition. Okay, I might state it wrong first. So let's say that I have an alpha Hölder. So it's a Hölder function with alpha as the exponent function between metric spaces. And let's say that A is a totally bounded subset of X. I want to relate the upper or lower Minkowski dimension of A and its image. Does any of you remember this, which way it goes? Okay, let's try. There are only two ways. So then some of you, well, one of your colleagues did this in the previous report, which I read just yesterday and checked, but I might mistake it. Okay, let's first try this. Okay, either this or it's the other way around. Okay, so I'm going to first try to do the proof, and then if it doesn't work, we're going to flip. Okay. Okay. So let's recall two things. What does it mean for F to be alpha Hölder? I have that if I were to look at the distances between two images, it's bounded by C times the distances between the original points to power alpha. That's the Hölder property. Okay, and for the Minkowski dimension, and similarly for lower. I'm going to use the standard definition of, or the initial definition that I gave for Minkowski dimension. So n epsilon of A is going to be the following. I'm going to fix an epsilon. Recall that n epsilon of A equals the min of the number of cells in some cover, each of whose cells has a diameter at most epsilon. M. C was epsilon, and then if I were to take the union of all the cells, I cover A. That's by definition. And I know that that's a finite number because I took A to be totally bounded. Okay. I think this is correct. So, the point is the following. If I start with some cover of A, let's say that has this property, then because f has Hölder property, I can control the diameter of the cells of the image covering. So here's what I mean. So it's a collection of subsets of X such that each cell of this curly C has diameter at most epsilon, and that it covers A. Define f of curly C now to be the cover or the collection of subsets of Y consisting of the consisting of the images of the cells of C under F. Okay, exercise. This is, well, let me just write it like this. So this is indeed a cover of the image of A. So second, well, the number of cells in f of C cannot be larger than the number of cells in C, because maybe f is so that some of the cells sort of like coincide when you apply f. Okay, now I want to figure out this bound. And I'll do that myself. So let me just do it here. I'm trying to bound this by some number. Okay, so this is the same thing as saying sup over C and curly C of the diameter of the image of C. And this is the same thing as this by definition. So the diameter of a set should be the sup of the distance of all pairwise of all pairs of points. Sup of y1, y2, and f of C. Okay, let me just leave it like that. dy, y1, y2. But then, of course, if I'm taking the sup over f of C as yi varies over f of C, I can rewrite it like this. Sup of C in C, sup of x1 and x2 in C of dy f of x1, f of x2, which then I can bound using the Hölder property. So this is bounded by some constant, which is, I guess perhaps this C is not a nice notation. Let's say gamma, which I can take out. D x, x1, x2 to the alpha, but taking the alphath power of something is a continuous function, which means that I can take this alpha outside like this, which means this is bounded by gamma times epsilon to the alpha. Okay? Which means that you see this number bounds from above the n sub gamma times epsilon to the alpha number of the image. This. But then if I were to take the min over all c's, this is going to give me n sub epsilon of a, because I chose the collection C so that that works. Now I need to take the limits. And then we're going to take a break. These calculations are not that sophisticated, of course. But maybe it might be bizarre looking if you're not familiar with these things. So I'm going to take the log of both sides. Now, I want this to converge to the Minkowski, which means that I should use this scale over here. And I have to use the same scale over here. Now, as epsilon goes to 0, gamma is a constant. This is going to give me upper or lower Minkowski dimension of, f of a. This is going to be a multiple of the upper or lower Minkowski dimension. Should be 1 over 2. Okay, so perhaps let's consolidate this. So this is log of n epsilon of a divided by, so what is this? This is minus log of gamma times epsilon alpha, which means I can write it like this. Log of 1 over gamma plus alpha times log of 1 over epsilon. Okay, that's a constant, so it's not going to matter. And when I take the limit as epsilon goes to 0, I'm going to get Minkowski of a divided by alpha, which is the Hölder exponent. And here I'm going to get the Minkowski of f of a. Let me just write like this, upper or lower. M upper, lower, m of a. That's the end. In particular, if I had a Hölder function, the image would have Minkowski dimension bounded by the image of the original guy. Okay. So you can, in practice, of course, you can black box this. Any questions about this? Okay, let's take a 5-minute break. We're going to keep working on these things. Okay, let's continue. In particular, if f is, you have a homeomorphism that is bi-Hölder, so f is Hölder and its inverse too is Hölder with the same exponent, let's say, then for any totally bounded A, you have upper and lower bounds on the upper and lower Minkowski dimensions of the image. In particular, if you have a bi-Lipschitz homeomorphism, that means alpha equals 1 here, the dimension, upper and lower dimension of the image is going to be exactly the same as the upper and lower dimension of A. In other words, upper and lower Minkowski dimensions are bi-Lipschitz homeomorphism invariants. Now, here's the next exercise. Let's look at shift spaces. That's the space of shifts, or sorry, space of sequences, one-sided, with symbols 1 to n. And we had these theta metrics. So n is a number that is at least 1, it's an integer. Theta is some number that is larger than 1. We had the d theta metrics. What was this? Discrete distance between the nth symbol of omega and the nth symbol of eta divided by theta to the n. No matter which theta you choose here, the Lebesgue dimension is always going to be 0. So, and it turns out, this is a calculation that I think is very good also, that the Minkowski dimension, upper and lower Minkowski dimensions are the same, and they're also equal to the upper similarity dimension, which is log of n divided by log of theta which in particular tells you that the Minkowski dimension does depend on the metric that you're using. So if I were to change the theta, any two such metrics are bi-Hölder equivalent or Hölder equivalent to each other, but they are not Lipschitz equivalent to each other. So you're changing the Lipschitz structure, if you want the smooth structure of the shift space, as you're changing the theta. But it's the same Hölder structure. Now, in this expression, if I were to take theta to infinity, okay, I just keep changing the metric, this expression certainly decays to 0. Okay? So that I have this. It turns out that this idea is true more generally. And that's a theorem that I think would be very nice for a final project. There is still some colleagues of yours that are deciding on what to study. So this is a theorem by Pontryagin and Schrinelmann. And they were able to relate the Lebesgue dimension to Minkowski dimension. Maybe I should say, first of all, that the Minkowski dimension, or lower Minkowski dimension, always bounds from above Lebesgue dimension. So that we have this too, of course. I'm just going to state it as a theorem. I think it's a beautiful theorem, but it's somewhat technical, possibly, and it will take some time. Pontryagin-Schrinelmann. For any compact metric space, I think totally bounded should be sufficient actually. Okay, I'll just leave it like that. For any x compact metric, the Lebesgue dimension is the infimum of all Minkowski dimensions, lower Minkowski dimensions, as you vary the metric. D is topologically equivalent to the original metric. So maybe I should say for any x d, d bar topologically equivalent to d. Very nice statement, I think. So somehow, you see, this is what is called a variational principle. This is like a purely topological notion. Doesn't depend on the metric. It depends on the topological type. And somehow, if you sort of optimize, an invariant that is in the Lipschitz category, smooth, once you optimize it, you get the topological thing. So this sort of idea sort of pops up everywhere. So for instance, there are different notions of entropy. There is something called topological entropy for a dynamical system. And there's a notion of what is called the metric entropy or Kolmogorov-Sinai entropy. And it turns out that, again, topological entropy, in this case, is going to be the supremum, but still, topological entropy is sort of the optimal value that you can get if you were to look at all different types of metric entropy as you change the so-called metric. In this case, it's going to be a measure, but still. Okay, so this is a very nice idea. So this is what is called a variational principle. Variational principle. And once you have something like this, you can ask many other questions, of course. For instance, here, the infimum was over not only d bars that are topologically equivalent, but in fact Hölder equivalent. So maybe you can do the same thing with d bar Hölder equivalent. I don't know if this is true, but it's a nice question. Another thing you can ask is that, oh, okay, so this is the infimum. Is it the minimum? That is to say, of course, in general, this is not true. Here's an example. But maybe for some metric spaces, it is indeed true that there is a remetrization such that the Lebesgue dimension equals the Minkowski dimension. And in particular, for instance, you can also say the following. This notion is always an integer. And this is a fractional value. And from this, you have the following statement. If you were to take a compact metric space, and if you were to vary the metrics on it that are topologically equivalent to the original metric, so that its dimension is the least, somehow that least dimension is always going to be an integer. It's a bizarre statement, if you want. Any questions about this? Now, later on, we're going to see that there's another notion of dimension that goes in between these two. It's going to be the Hausdorff dimension. But if this is true, certainly you can optimize the Hausdorff dimensions as well. And the infimum of the Hausdorff dimension is going to be the Lebesgue dimension too, as a corollary to this. As usual, I've put the original paper in French of these two people. Under the resources, I've put also a translation of it. And Pessin and Klimenhaga, in their book, they also kind of mention why this is sort of like a nice theorem. Okay. Any questions? Let's now sort of relate this to the Moran-Hutchinson formula. I'd like to give a heuristic as to why at least the Minkowski dimension count is true. Next week we're going to prove some version of this for Hausdorff dimension. But still, I think it's good. Heuristic for the Moran-Hutchinson formula. For Minkowski dimension, let's say. Recall the following. The Moran-Hutchinson formula basically says the following. If you have a nice B-IFS, its upper similarity dimension is the same as any other dimension, pretty much. B-IFS with unique attractor A sub W. And so the upper similarity dimension of W was the following. Is the unique number T that solves the following equation, such that if I were to take the sum of all the Lipschitz constants to the power T, I want that to equal to 0, to equal to 1. 1 to n lip of Wi to the T equals 1. We discussed how, this has a unique solution T, so that T is the upper similarity dimension. That's a number. In a sense, compared to other notions of dimension, you see, this is rather straightforward to compute. We're just solving an equation, basically. So I want to have a heuristic for upper similarity dimension being equal to the Minkowski dimension. So Minkowski dimension of the attractor. So let me write it like this. If the iterated function system is nice, whatever that means, so maybe totally disconnected and blah, 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 you're going to get to that later. So if this is nice, then the Minkowski dimension of the attractor is equal to USD. This is what I want. Now you should think of, by the way, this part as sort of a template for your presentation as well. Like when you're writing the final report, obviously you're going to have more details, but your presentation is going to be like 6 to 10 minutes probably, and so you're not going to be able to go too much into detail. You don't have enough time, and people have a certain amount of bandwidth. which something that I'm aware of, even though perhaps it's not clear sometimes. But so it's better to give some idea. You see, I just like say nice. I don't care what nice is. I'm just saying it's nice. Of course, the Cantor should be nice and blah blah blah, right? I'm just saying this is the idea. So you should sort of think of this part of today's class as sort of a template for how to give a talk. And then, of course, if someone asks, oh, what do you mean by nice? Then, of course, you need to know what nice means. So you cannot fake it, but you need to be able to speak in a vague language, but if needed, you need to be able to make it more formal on the spot. Or you need to learn how to not answer. You need to learn how to be a politician. I think in this class I've given examples of that too. Of course, I have authority as an instructor, so I can just say it's an exercise now. So, okay. So we're going to use the original intuition for this Minkowski dimension. So here's the idea. Recall the intuition was this. Number of pixels times scale, or 1 over scale, I guess it doesn't matter. Scale of pixels to the d, that's the Minkowski dimension, should be a constant. It should be a constant in the scale. Okay, so if I were to take an epsilon, that means that an epsilon of A is C times, what is it? So epsilon to the minus D. Oh, sorry, epsilon to the D. So this scale should be 1 over epsilon here, if you think about how we sort of derive the definition and so on. Now, because this iterated function system is nice, so A sub W, of course. Say it is a totally disconnected iterated function system. Well, first of all, A sub W is the unique solution to this. I look at the images and then take the union. Okay? Now, let's say that my iterated function system is nice, so that each of these pieces are disjoint. Now, if I have disjoint, compact, and non-empty open subsets, compact and non-empty subsets, the distance between them is positive. That is to say, so this, so let's say like this. Distance between this and the jth image, of course the Pompeo-Hausdorff in the Pompeo-Hausdorff sense, this is bounded from below by some epsilon 0 for any ij. Not equal to each other. That means that if I were to take my epsilon, my scale small enough, the n epsilon contribution coming from these different pieces are not going to contribute. Right? They're not going to sort of overcount. That is to say, if my pixel size is very small relative to this number, this is equal to the sum of all n epsilons of the images. Okay? 1 minute. Okay. Now, Wi, again by niceness, is sort of, it's a contraction and it's sort of like a uniform contraction. It's a similitude if you want. That means that the image, so the number of things I need to use to cover one of these images should be proportional to, what is it? Lipschitz constant of this times n epsilon. Okay, now this equals this, and I see another copy. Okay, so C times epsilon to the d equals this guy, which equals sum from 1 to n of lip Wi. I need to have something here. So this should be divided by Lipschitz Wi. I think this is correct. Times C times epsilon over lip Wi to the d. Okay, I'm not going to continue. I'm going to finish this next week. I don't want to rush it because I think I'm making a mistake somewhere. But anyway, this is sort of like where you go. And ultimately, if you sort of complete this heuristic, you do get the Moran-Hutchinson formula. Okay, thank you. I'll see you next week.